Okay, today we are on lesson 5.1.3 and it is going to introduce you to something called inverse trigonometry. So far you've learned two new tools in this chapter. You've learned about cosine and sine ratios that deals with different parts of a right triangle and using those ratios to look at the appropriate lengths and solving for the missing lengths of a right triangle. And of course, last chapter you had tangent. So now you have a complete set. You have cosine, sine, and tangent. You have all these three tools that you can use to figure out different sides of a missing right triangle, right? But now let's go backwards a little bit and see what we can do. We can use these tools a little bit more, but in a slightly different way, all right? So let's explore. Number 24 here says, Mr. Gao needs to build a wheelchair access ramp for the school's auditorium. The ramp must rise a total of 3 feet to get from the ground to the entrance of the building. In order to follow the state building code, the angle formed by the ramp and the ground cannot exceed 4.76 degrees. Now, is this true? I don't know, but there must be some sense to this, right? If your ramp is too steep, then of course the wheelchair has a very hard time to get up. So there must be some sort of regulation to make sure that your ramp is a steady and comfortable enough ramp, that an incline, so that the wheelchairs can go up at a very, very good speed and not go up too fast and not fall off the ramp, right? So you want to make sure this is actually something that is able to be used, right? So Mr. Gao has plans from the planning department. It calls for the ramp to start 25 feet away from the building. Will this ramp meet the building's state building code? Draw an appropriate diagram. Add all the measurements you can. What does Mr. Gao need to find? So let's see. The ramp must rise a total of 3 feet to get from the ground to the entrance, right? So I'm going to zoom in a little bit here and kind of show you what we're talking about. So here is the ground, right? And here is the building. And I think the doorway is right here. The doorway has to be a little bit above, right? So this is my door. I'm going to do a little doorknob here to open the door for you. And you can see this is 3 feet, right? What am I talking about this? So this piece right here, that's 3 feet, okay? Now, it says he has the ramp to start 25 feet away from the building. So if he's going to put in this ramp, I'm going to use different colors so you can see the ramp itself. He has this ramp all the way out here. So this is the ramp, right? He is trying to build a ramp here so that the wheelchair can go up this way, right? So how far away is this ramp? This ramp is 25 feet away. Okay, right here. Okay, so it's 3 feet up and 25 feet away. And it says, the angle formed by the ramp, so I'm trying to read this line right here. The angle formed by the ramp and the ground. So the ramp and the ground cannot exceed 4.76 degrees. So where the ramp and the ground meet is right here. So that's your angle. This is the angle we're looking at. This part right here, that's the angle theta. We call that theta. Theta is a variable we use very often to represent a missing angle, and it's simply just a 0 with a bar through. It is a Greek letter that is used very often, and you might want to get comfortable because you're going to see this a lot in future classes, all right? Okay, so it says, what does Mr. Gao need to find? Well, then Mr. Gao needs to find that angle, right? So Mr. Gao, let's answer the question first. Okay, apologies, try again. He needs to find the angle between ramp and ground. So he needs to find theta. In parentheses and put theta. So again, I just put a little circle with a bar through, okay? To find from a trigonometric ratio, you need to undo it. To find angle, sorry, I think there's missing a word here. To find angle from a trigonometric ratio, you need to undo it just like you can undo addition with subtraction, multiplication with division, or squaring by finding the square roots. So how do you undo it? You do this thing called inverse operations. So some of your teachers may have already talked about it, which is awesome. If not, this is something you might want to highlight like I did here, the inverse operations. So find your scientific calculator. You need a scientific calculator that has a tangent, these trig ratios. Sometimes the trig ratios are hidden, so you might have a button that says trig, and you gotta push on it a couple times and this will show up. All right, but take a moment. Some of your buttons will say sine, cosine, tangent, and up on the little corner there, if you hit second, and it becomes the sine inverse, cosine inverse, tangent inverse, right? So sine inverse, cosine inverse, and tangent inverse, right? So verify that your calculator can find the inverse trig values using the triangle on right, all right? So right now we're taking a pause from Mr. Gal's problem and trying to show you how these tools work, all right? So it says, when you find cosine inverse of 8/16, what do you get? Well, first of all, cosine is adjacent over hypotenuse. So the cosine ratio is 8/16, right? So technically, when we write this out, we really write this as a problem. We're going to write and say, well, cosine of what angle is equal to the ratio of 8/16. And so in order to solve for that what angle, you use this inverse. You're trying to undo the cosine. So that's why you're trying to do this cosine inverse of 8/16. All right, so same with you. I have a graphing calculator, so I'm going to use my graphing calculator here. In fact, I'm going to run the risk of this. I'm going to show you. Okay, so first things first, you want to make sure your mode is in the correct form, right? We did this before, and if you haven't touched it, don't worry about it. If you did, then make sure you change it, but go to mode. Notice over here it says radian and degree. I want to make sure it's in degree, so mine is in degree. Yours may be a little bit different, but make sure the word degree is highlighted, okay? All right, so now cosine inverse. Notice over here, this is my cosine button, but there's a little highlight here, this upper corner, that's inverse. So second cosine inverse of 8/16, close your parentheses, and then you push enter, you get 60. And that's exactly what we wanted you to see. All right, so if we go back to our problem here, see, the angle is 60 degrees, right? Because look at this triangle here. It says the angle is 60 degrees, and that is the ratio that gave me the angle of 60 degrees. So when you punch it in a calculator, you get 60 degrees, okay? All right, so the inverse button gives you that missing angle, okay? But you need to know which trig ratio you are using. So it says, return to the diagram from part A. According to the plan, what angle will the ramp make with the ground? Will the ramp be to code? So first thing you want to look at is this triangle here. In this triangle, what do you have, right? And it's a little messy here, so we have a little bit more room. Well, not really, but I'm going to redraw this just so we can see a little bit better, okay? Okay, so we're going to return to the diagram from part A, and the diagram, I'm going to draw it again just so we can see a little bit better. You have the length here as 3 feet, and you have the length here as 25 feet, right? And here is your triangle that is being created, and this is your missing angle theta. Okay, all right, so based on what I have here, this is where the right angle is being created. So based on what I have here, I have opposite and I have adjacent. Why is this important? Because it tells you then we need to use tangent, because based on SOHCAHTOA, based on the fact that you have opposite and adjacent, your ratio is going to be a tangent ratio. So the way you set this up is you say tangent of the angle is equal to opposite over adjacent, right? Now, just like solving for a variable, you're trying to solve for this theta, right? You're trying to get rid of the tangent, you're trying to move the tangent. So in order to move it, you got to use the inverse. So the angle is equal to tangent inverse of 3/25. Okay, so I'm going to use my calculator over here on the side here because I don't want to go back and forth between the screens. But if I go tangent inverse of 3/25, that will give me a lovely, and you should be getting a decimal that doesn't end, right? So it's going to be super duper long, but it should be 6.843. So for trig ratios, if you're using a trig ratio, you really want to keep your decimals a little bit longer. So 2 or 3 decimal places is good, all right? So it's about 6.843 degrees. Is the ramp up to code? The code says you cannot be more than 4.76 degrees. We are 6.84 degrees. We are way too high. So the incline is way too steep. The wheelchair might fall off. So no, ramp is not to code. Okay, all right. Okay, so now it says, so Make sure as you answer, note ramp is not up to code. Sorry, the screen wasn't sharing for a little bit. Okay, so now at least how far from the building must the ramp start in order to meet the building code? If Mr. Gal builds the ramp exactly to code, how long will the ramp be? Show all your work. Okay, so now we're gonna make the distance longer, because think about it. Let's take your ruler and just kind of try this out. This is the ramp. Pretend this is a ramp and this is a doorway, right? Here is your ramp. If it is a shorter ramp, I'm closing it off with my hand here. If it's a shorter ramp, notice how it's a little steeper, right? But if it's a longer ramp, you can make this a little bit less steep. So the angle is smaller as your ramp is bigger, longer and versus shorter, right? So shorter ramp is a very steep ramp, but if it's a longer ramp, it's a lot less steep, right? So it means the angle is a little bit smaller. So let's draw the situation again. What we know is what's not going to change, this distance to the door. It's still going to be 3 feet. Okay, what is going to change? Well, I don't know how far to make the ramp, right? Because I'm going to make this length a lot longer. So that's what I don't know. What I do know is in order to make this up to code, that angle has to be 4.76 degrees. I'm going to check real quick again, make sure I remember that right. Yes, 4.76. Okay. Now, based on this picture, I still have a tangent ratio because I still have the opposite and adjacent. But this time, a little bit different. I have the angle, I have a missing side. So we're going back to what we're comfortable with. So I'm going to say tangent of this angle of 4.76 is equal to opposite over adjacent. And if you recall, if our variables on the bottom, we got to swap the denominator with the left side. So it's going to be x equals 3 over tangent of 4.76. All right, 3 divided by tangent of 4.76. And that'll give me 36.028. Okay, so based on calculations here, we see that the x is 36.028 feet. That means the ramp must be at least another 11 feet farther away from the door, farther than what Mr. Gao originally planned. Mr. Gao originally wanted 25 feet away, but it has to be at least 36 feet away, right? So this measurement is for how far away. How far from the building must the ramp start? So that's actually the first question here, all right? So second question, how long will the ramp be? Well, the ramp itself is actually this length right here. This is the ramp, right? So now you have a couple of tools now. Because you have the 2 missing sides, you can go ahead and use Pythagorean theorem and figure out how long that ramp is. That is your hypotenuse. Or you can still use trigonometric ratios. You can still use, in this case, we are going to look at this side that we know and the hypotenuse that we don't know. And so when we have opposite and hypotenuse, this is going to be a sine ratio. So let's practice using the sine ratio, all right? So sine says opposite over hypotenuse, all right? So hypotenuse, all right? So I'm gonna say sine of 4.76 equals opposite over hypotenuse. Let's use h for hypotenuse as how long the ramp is going to be. All right, very similar to what we had before. Actually, if you look at the equation next door, it's exactly the same, except this time I'm using a sine ratio, because sine is going to use the 2 very important parts of opposite and hypotenuse, versus tangent is using opposite and adjacent. All right, so now my variables on the denominator again, I'm going to swap them around so that I get h equals 3 over sine 4.76. Okay, now let's punch that in the calculator. Again, we're not using inverses. We're just going to use our regular trig ratios. Punch that in, and that's going to give us 36.15. So 152. So a little bit longer than my previous answer, but yes, because your ramp isn't 4 degrees is really not that much. So when it's not that much of a difference, then your hypotenuse and your leg is going to be very, very close to each other. But again, your hypotenuse should be longer, because hypotenuse should always be the longest side of a right triangle. All right. So let's answer all the parts to this question. All right. So make sure you answer all the different parts. So how far from the building? So the ramp must be 36.28 feet from the building. And it must be itself, the ramp itself must be 36.152 feet long to meet the building code. Okay. All right, so again, there's two parts to the questions here. It's asking you, first of all, how far away from the building, and then how long the ramp itself must be. Okay, all right, let's look at our second part of our notes here. I gave you some really good diagrams here, right? So before we go there, let's move on to the next question here. For the triangle on the right, find the measures of angle A and angle B. Once you have found the measure of the first acute angle, either A or B, what knowledge about the angles in the triangles can you help to find a second acute angle? All right, so typically when we do this, I don't want you to do what they're saying to do here, so just kind of hold off on that, all right? So pick an angle you want to figure out, right? So I am going to pick A. I can do B if I want to, but I'm gonna pick A for now, okay? Now, whether I'm at A or not, it doesn't matter, because it doesn't matter which angle I pick, the hypotenuse will always be 15 in this case. This is always hypotenuse. That side, because it's always across from the 90-degree angle, it's always going to be a hypotenuse. What changes is which angle you pick. If you choose A versus you choose B, your opposite and adjacent is going to be a little bit different, right? Choosing A, that means this must be my opposite and this must be my adjacent. All right, so based on what I see in this picture, I have hypotenuse, I have adjacent. That means I'm using cos, C-A-H. That means cosine equals adjacent over hypotenuse. So that allows me to solve for this. I say cosine of angle A must be adjacent over hypotenuse. And again, to solve for angle A, we're going to use the little inverse function because I'm trying to get rid of it. I'm trying to do the opposite of the cosine. So A equals cosine inverse of 14 over 15. All right, using my calculator, cosine inverse of 14 over 15, that gives me 21.039 degrees. Okay, now your book is saying, hey, if you got the angle, you got angle A, and you know this is 90 degrees, you could figure out the third angle. But I wouldn't recommend you to do that, because if you do it that way and you got the wrong answer for angle A, your angle B is going to be wrong too. So what I recommend you to do is, okay, start new again. Start this problem new. What do you mean start new? Start now by looking at the different angle. I'm looking at angle B. But notice how I did not erase the hypotenuse, because it doesn't matter which angle I pick. That side at 15 is still going to be the hypotenuse. What is going to change is now the 14 is going to be my opposite, and now this is my adjacent. So this problem now becomes opposite and hypotenuse, O and H. So that's the SO part of it. SOH, sine is equal to opposite over hypotenuse. So I'm going to use that idea and say sine of angle B is equal to opposite over hypotenuse. So angle B is equal to sine inverse of 14 over 15, right? All right, see how I'm using a different ratio this time because I am using a different angle. So the ratio must be different, or at least the trig ratio. The trig tool that I'm using is different. You punch it in, you get B is about 68.961 degrees. Okay. Now, this is where I want you to use the knowledge of the fact that triangles all add 180 degrees. If you take these two angles, 21.039, and add up to the other angle, 68.961. And then don't forget, you have a 90-degree angle in this triangle. You should get exactly 180 degrees. That's how you should use that 180 to check, right? Don't use one of the angles to solve for the other angle, because that's going to be what I call a domino effect. If you miss one, you're going to miss the other. But if you do it this way, then you can use your trig knowledge to see if you got one wrong, and you can fix your mistake right away. Okay, all right, so this is what we were talking about. And again, if you've already heard this like 3,000 times, don't worry, it doesn't hurt to see it again. But this is what most teachers are talking about when they say, oh, so ka toa, right? So here's your so, S-O-H, so, S-O-H, ka, C-A-H, so ka, and toa, right, T-O-A. So ka toa, it's kind of a quick little acronym to help you remember all the different trig ratios, right? So is SOH, sine is opposite over hypotenuse. Ka is CAH, so cosine is adjacent over hypotenuse. And then toa is tangent is opposite over adjacent. Okay, so with the three tools, now what you need to figure out, what are you supposed to use in each of the situations. Okay, so first things first. What I do is, whenever I see a triangle, I always start off by labeling the hypotenuse. It doesn't matter where my angle is, the hypotenuse will never change. So first thing you should do when you approach A, B, and C, just go ahead and label all the hypotenuse. So I look at this and go, okay, 90 degrees. Okay, this is a hypotenuse. Okay, this is the hypotenuse, and this is the hypotenuse. Okay, done. Next, look at where your angle is, and now figure out what's your opposite and adjacent, right? So if this is the angle I'm using, and since this 12 is touching my angle, this is going to be my adjacent. I don't have an opposite in this case. Don't need to worry about it. Okay, we'll deal with that in a minute. Move on to the next piece. Your angle's here, theta is here, and I have opposite here, and I have adjacent here. I actually don't have any information for the hypotenuse, so I can go ahead and erase that. But I had to put that hypotenuse in there just in case you think that's the adjacent, right? So if I had the hypotenuse there, you wouldn't confuse yourself and say which one's adjacent, because both sides are touching the angle. One of them must be the hypotenuse, then the other one must be the adjacent, okay? All right, this angle here, the other side over here must be the opposite, so that's your opposite, and then adjacent has nothing, so I'm gonna leave it at that. So see, now you actually have your problem already set up so that you know exactly which trig ratio to use. For example, in part A, I see A and H. Well, if I look at my SOHCAHTOA, the only one has A and H is cosine. So I know automatically in this case, I write cosine of the angle is equal to adjacent over hypotenuse, right? This is why labeling the sides really help, because it tells you exactly which trig ratio to use in this case. Okay, now, same as before, you want to move the cosine over, so it becomes cosine inverse because you're solving for an angle, and then you punch it all in, so you get 12, cosine inverse of 12 over 24, that would give you 60 degrees. All right, you're lucky. It doesn't always end up in a very perfect number. In fact, it rarely ends up in a perfect number. So just kind of watch out for that. Actually, in two of our problems, we're very lucky in the first two problems are going to end up with perfect numbers. All right. But don't expect that every single time, because there are so many possibilities in our angles. So perfect trig ratios are very rare. Okay. All right. Next problem, I see the letters O and A. So if I look at my ratios here, the only one with O and A is TOA, which tells me I need to use tangent. So I go tangent theta equals opposite over adjacent. So then that's tangent inverse of 8 over 8. That will give you 45 degrees, perfect 45 degrees. Okay, last one, I see O and H. So O and H is so it's sine. So sine of 57 equals opposite over hypotenuse. See how my x is on the bottom? I'm going to swap the whole thing. So x equals 7 over sine of 57. So 7 divided by sine of 57. I get about 8.347. And that's how long x is. Okay, so I'm going to pause for a second here, and you might want to write this down yourself. Please take a minute to note this. In parts A, B, and C, in parts A and B, you're solving for the angle. Notice when we solve for angle, we need to use the inverse, that little -1, the little inverse, right? But in part C, we're solving for a missing side. We don't need to use the inverse. So the inverse is only used when you're solving for a missing angle. Never use that when you're solving for a missing side. So that may be helpful. Okay. All right. Peter cannot figure out what he did wrong. He wrote the equation below to find the missing angle of a triangle. Okay, he's trying to find a missing angle. So remember what I said, when we're finding missing angle, we must use the inverse function. So we must use the little -1. However, his calculator gives him an error message each time we try to calculate the angle. Okay, so Peter says cosine theta. So naturally we would say, okay, to solve for theta, it's cosine inverse of 8 over 2.736, right? Try punching in the calculator. What do you see? You should see an error message, right? So something's wrong. Okay, so what's wrong? Jerry says, his teammate looked at his work and exclaimed, of course your calculator gives you an error. Your cosine ratio is impossible. What is Jerry talking about, and how can she tell? Well, let's see, what is a cosine ratio? Cosine is adjacent over hypotenuse. Well, in our case, in Peter's case, he says then this is adjacent and this is hypotenuse. Something's wrong with the picture. Didn't we say hypotenuse must be the longest side of the triangle? So how can the adjacent be longer than the hypotenuse? right? So that's what Jerry's talking about. The ratio, he probably flipped it around. He probably put hypotenuse over adjacent. That's why it's giving you an error message, all right? So I would say cosine should have adjacent over hypotenuse, but, okay, you know what? Hold on. Terrible writing. Haven't written in a while. So, but Peter's hypotenuse is less than the adjacent. Not possible, right? So that's a very key thing you want to watch out for when you're dealing with these, all right? So most important thing is make sure you have your sides labeled correctly. Who is a hypotenuse first? That's the very first thing you want to label. Then based on the angle you're at, which one's the adjacent, which one's the opposite. Once you have that, SOHCAHTOA will really help you figure out which ratio to use. Okay, that's it for today.